Thank you, Tim, and welcome everybody to this session coming from the UK. It's about 8:30 at night at the moment. We'll run through till about 10 to 10, which means about 80 minutes of your time. Now, I've just started a stopwatch here, which is large enough for me to read. So probably after about 40 minutes, about halfway through, I'll just take a short break so that you can just stand up, stretch legs, leave the room if you wish to leave the room, but it'll only be 2 or 3 minutes, just for a moment to pause and relax and stop thinking, stop concentrating briefly. So my topic for today, I've got 64 slides. Some of them are demonstration type slides to clarify or emphasize a point. So if it looks like I'm running out of time, there will be a few slides that I can quite easily skip over. I just make a statement about some observation and then say, and these slides would have demonstrated it. So we don't have to spend time necessarily on every slide here. I will be sending Tim a PDF file of the slides so you can pick them up later. So object statistics, when object statistics aren't enough, that's the aim of the title. And really what I'm going to talk about is the many different ways in which things can go wrong, and not just be wrong permanently, but perhaps suddenly go wrong for no apparent reason. And very, very often there is some feature of object statistics which is underneath a performance problem that you're seeing, typically because an execution plan has changed. So the big aim really behind this presentation is to show you a large number of cases where things go wrong so that you might recognize patterns. Now, very few people need to know everything I'm going to talk about. In very, very few cases will you actually come across specific examples where a particular problem has appeared. But it's nice to be able to say, gosh, something happened last night, this plan now looks like this, or something happened at 1 o'clock this afternoon, this plan is now very bad. Why has that happened? And you may, because of this presentation, spot some sort of pattern, some sort of symptom which looks familiar and gets you moving in the right direction to decide what is the problem. And there will be, towards the end of the presentation, some ideas and comments and thoughts about the types of things you can do to deal with problems which are basically built into the optimizer. Okay, so when object statistics aren't enough, we'll start with just a quick introduction to me. So there's my independent consultant bit. I've now been using Oracle for more than 30 years. I do troubleshooting and short-term stuff in general. There's a few little recognition points that have come up, and yes, at the bottom there, grayed out, is my O1 visa for the USA, which gave me that wonderful description. Books which I've contributed to, books which I've been the sole author about. And of course, the CBO book there sitting in the middle is now about 12 years old, I think, or 13 years old. I'd really like to update it, but there's just so much one could write nowadays. It's basically impossible to do a good job, I think. So, statistics, the problems of using statistics. There's the problems you can have gathering statistics, and then one way to solve almost all the problems I'm going to talk about, how you fake statistics, how you avoid spending effort gathering them, how you avoid having to run the risk of instability causing performance changes due to plan changes. So 3 big sections to run through. And we'll start with the problems of using statistics. Now, I guess that at least some of these problems are fairly well known to most of the audience, but we'll still go through them. First of all, there's the problem of out of range. What happens when you query for data and your predicate says, give me the data that the optimizer thinks isn't in the database? I'm querying for a column value which is outside the low-high range. So a little demonstration here of how Oracle handles that problem. You'll see I've got 100,000 rows in my table. And here I've got an N1 column which has 1,000 distinct values. My mod function gives me the values from 0 to 999. I've got 100 rows for each value. So having created that data set, I'm going to run a few queries. So first I'll run a query which says select where n1 is 499. That's right in the middle of my range. Then I'll do it select where n is a bit bigger than the high value that the optimizer knows about, and then select where n1 is a lot bigger than the value that Oracle knows about. And I'll show you the execution plans, showing you particularly the cardinality estimates. It's always going to be a full table scan here, by the way. I haven't got any indexes. What I'm only interested in here is cardinality, number of rows. So here we've got rows. When I have my first query, n1 equals 499, Oracle's estimate is 100 rows, which we can see just here. So Oracle's got a good estimate. Well, it's very simple data, very simple query. If we move to the n1 equals 1200, what happens to that estimate? It's dropped down to 80. And then we go to n1 equals 1500. Oracle's estimate has dropped down to 50. And the further away we get from the known high value, the smaller that estimate will become. Now, what this means in a production system, of course, is that you could find that you've got perhaps just a couple of tables, a couple of columns where you run this sort of query where there's a time-dependent pattern to the data. Some value keeps increasing, and people are only interested in the highest values. And as time passes, they're automatically going to be querying for data which is outside the known range. Now, in many, many cases, you'll have something which says, oh, we gather stats regularly, and Oracle keeps refreshing stats. So while we go outside the known range, we're never a very large fraction outside the known range, and therefore we happen to be safe. But of course, you may find you've got a few places where you very rapidly go outside the known range and go quite a distance outside the known range, but you aren't collecting or refreshing the stats fast enough. And suddenly, for no apparent reason, one day, someone runs a query and Oracle says, gosh, I'm a long way outside the known range, bang. You're going to get a small estimate here. Because you get a small estimate on this table, the execution plan changes for the rest of the query. So that's the basic threat. We can draw a little picture of this, by the way, just to show you how Oracle is thinking, the image behind the arithmetic. When Oracle has very simple data here, it's a uniform distribution of data. We've moved from a low value of 0 to a high value of 999. And very uniform data. We have 100 rows for each value. Oracle takes this picture and says, okay, let's extend backwards, let's extend to the low values the same distance to get us down to 0. So it produces this angled line down to 0, which is 999 to the left. It does the same thing to the right. Extend the range, 999 steps, the same distance again to the right, and then that's how we come down to 0. And this is what I describe as the linear decay approach that Oracle takes. So when we asked for value equals 499, Oracle's quite happy to say, yes, it's 100. When we go for, what was it, 1200, that's the picture that Oracle produces. It goes on this graph over to 1200, up to the slope, hits the slope, comes across and says, oh yes, that's 80. And roughly speaking, you can look at the two areas I've highlighted there, which says 999 to 1200, that's about 200, divided by the entire range is about 1,000. We reduce by about 200,000, about 20%. When we go out to 1500, same thing happens. Oracle says, okay, from 1500, go up, go across. We've dropped by about 50%. And the distance we are outside the range, that 500 extra, is about 50% of the existing range. So this is how Oracle does its basic calculation for column equals constant when you move outside the known range. If you just want the formulae, that's just them there in the top right-hand corner. So that's one of the out-of-range problems, column equals constant. Things can actually get much worse. What happens when you start running queries which say column greater than? Now this does come up, again, it tends to be time-based or sequence-based data where you can run into this problem. So here's a little model which actually represents roughly a problem a client had some time ago that I went in to see. We've got here a table, again with my create table, I've gone for 100,000 rows here. This expression I've used here, sys_date plus all the bits and pieces, well, 86,400 is the number of seconds in a day. I've got row number divided by 3, divided by 86,400. What I've got here is a data set where I've got roughly, well, actually almost exactly 3 rows per second going 100,000 rows into the past. That's about 33,000 seconds into the past. That's about 9.5 hours. Okay, sorry, 3,300 seconds, 9.5 hours. But we've got here 3 rows per second. Now I'm going to gather stats on this data, and then I'm going to say to Oracle, show me the data which appeared in the last 5 minutes. So in my query here, I've actually put in a little hint-like thing which says 2 seconds later. So immediately after I've gathered stats on this data, immediately after I created it, I say, show me sys_date minus, well, 5/144 is 5 minutes ago. Okay, 5 minutes at 3 rows per second is about 900 rows. So here we go, Oracle says yes, 888 rows. Okay, so it took me a few seconds to gather stats and then run that query. I'll just sit back and twiddle your fingers for 5 minutes and wait and run another query. So just over 5 minutes later, you run the same query, sys_date minus 5 minutes. But we've let time pass and I've kicked the previous cursor out of shared pool, so Oracle's going to re-optimize this statement. More than 5 minutes have passed, so now what we're saying is, show me data where the place date is greater than the known high value. What does Oracle think you'll get? 3 rows. What it's given you is the cardinality of column equals constant. Our data set has 3 rows per second. Any one value appears 3 times. It's the column equals constant. Oracle takes this thing when you go out of range with inequality. Oracle just says, okay, you're outside the range. Only a tiny bit outside the range, but bad luck, column equals constant. That's how I'll do the arithmetic. It's amazingly silly, in my opinion. I mean, it's extremely dangerous. It's totally inconsistent, really, with the way Oracle behaves for the column equals outside range value. So this is a much bigger threat. And perhaps it won't hit you often, perhaps it won't hit very many of you, but this is something that's worth knowing. If you set a high value and then query for inequality greater than high value, a short time later, Oracle can come back with a remarkably silly estimate of cardinality. Now, the big picture of how you deal with both these out-of-range problems is simply to say, you can't gather stats to solve this problem. You can write a little program which says, set column stats. I will set a high value which stops the accident from happening. So quite literally on one site, they've got a little piece of code which says, every hour on the hour, set the high value on this column to now plus 65 minutes. And then whenever people are querying that data, they're always within the range because they're always saying, what happened just a little while ago? So we just solved this problem by not letting Oracle gather stats here. The moment Oracle gathers stats, it's already starting to be wrong. We have to have a different mechanism. One possibility is just to say, there's a couple of special cases where we will set column stats. Now, in the same range, same sort of area as you get this problem of going out of range, of getting bad estimates when it's unreasonable, here's another problem that's getting bad estimates, and there's very little you can do about it. What happens when you have subqueries? So I've created here, very compact, I've got a table, I've just gone to all objects and said, copy the first 20,000 rows. And I've created an index on the column owner object ID. And I've gathered stats. And I've gathered stats on the index as well, cascade true. So now I'm going to run a query, which I think you can all work out the answer to. Select from this table where the object ID is larger than the maximum object ID in this table for sys. Well, we're obviously going to be looking at something which says, don't really know what that's going to give us. But we know we're looking at a max object ID for sys, or virtually everything at the first 20,000 rows in my system is sys. We're going to be looking at some of the very, very big object IDs here. We're probably going to find a very, very small number of rows. So what does Oracle actually say at this point? It says, I'm going to estimate 1,000 rows. And that's a fixed percentage. When you give Oracle a query of this type, the select where greater than subquery or select where less than subquery, Oracle simply says, I've got no idea whatsoever, let's call it 5%. And so you can end up with queries where literally you know roughly the amount of data you're expecting to get. Oracle simply says, yeah, bad luck, I can't work that one out, 5%. And again, you can't solve this problem by gathering stats. In fact, in this particular case, you've really got two strategies available to you. One of them is simply to say, I know what the execution plan should be. Because I know you're going to get the numbers wrong, I will have to create a plan and fix a plan and say to Oracle, this is the plan. This is how I want you to run this query. Alternatively, you go to the SQL tuning tool and get Oracle to examine what's going on, and Oracle will create a profile which says, oh yes, where I guess 5% normally, I'm going to take that number and I'm going to scale it down by a factor of 326. And basically Oracle will say, I will add in this profile an opt estimate hint. An opt estimate hint which says, for this table, I'm overestimating or underestimating dramatically. This is how you fix the arithmetic, right? So if you haven't paid the license for the tuning tool, you write the execution plan, or you could start worrying about putting in your own opt estimate hints or your own cardinality hints. Neither approach there is actually really supported or approved of by Oracle Corporation. Okay, so that's ranges. What else goes wrong? Well, I think function of column. That's another place where Oracle simply guesses. So I've got here a table. I've got 10,000 rows in this table, and all I've done is take row num and cast it as a number. Okay, so let's take a very simple function. Mod of ID, 2 equals 0. Well, the mod function says that this value, this function, is either going to return, in this case, a 0 or a 1. So 50% of this data, half this data, 5,000 rows, will satisfy that predicate. Okay, what does Oracle say? 100 rows, because it's guessing. Oracle has no idea what the impact of the mod function will be on your data. So just as we have a 5% guess with subqueries, Oracle says function of column equals constant, let's call it 1%. If you go for function of column is greater than or less than constant, we'll guess at 5% again. Function of column is between a couple of values, it's 0.25%, 5% to 5%. So Oracle basically guesses. And again, there is no way around this. You can get lucky. People often get lucky, and guesses which are really quite bad guesses aren't so extreme that you get really bad execution plans, but sometimes they are. And if they are, sometimes you either hint the code, construct a plan that you want to see, put in the hints which make that plan happen in various ways, or you start feeding in opt estimate or cardinality hints to say to Oracle, you're making a bad guess, right? But function of column, that's another great way in which Oracle does things which are extremely unpleasant. Okay, things that you can sometimes do, this is not guaranteed to work, you may not be able to find a way of expressing it. One of the very nice things in Oracle 12 particularly, we can start creating virtual columns. So in this particular case, I've said, let's add a virtual column to our table. And because it's 12C, I've been able to say, and let's make this column invisible. The nice thing about doing that is that any code which just does an insert without specifying a list of columns simply doesn't know that this column exists. So existing code will carry on working even though this column is here. You could add virtual columns in Oracle 11, but you might then find that some code which does insert without specifying column names crashes because it says you haven't matched up the right number of columns, the number of inserted values, or your inserted columns here are not compatible with this table because you're trying to insert into a column which is a virtual column. So virtual columns may be very helpful. Invisible virtual columns are really quite terrific. Now, having created this virtual column, I've got to create stats on it. So I've just run a gathered stats here, gathered table stats, just as a reminder to say you've got to have the stats. And once we've done that, this is just the same query I had before, right? Notice I have not changed the query at all. So what does Oracle do with this completely unchanged query? It says, hey, that expression that you've got in your query matches an expression I've got for a virtual column, so I will replace your predicate with the virtual column, and then I'll optimize the query. And we get here, Oracle says, yes, this query is going to return 5,000 rows, and look, the predicate is about the virtual column, it's not about the function. So whilst there may be lots of cases where you have to do something really messy with plans and hints and opt estimates and all the rest of it, you may find that you can construct a virtual column which maps the predicate that you're really interested in, make it invisible, and you find that once you've gathered stats on it, the optimizer can use the stats about your virtual column when handling that particular predicate. Now, there are various ways in which you can manage to implement this type of approach. The virtual column that you've labeled invisible in 12c is the nicest way of doing that. Okay, next problem. I think everyone knows about this one. It's the correlated columns. If we have two predicates on a table, select where predicate 1 and predicate 2, Oracle simply says, well, I've got two separate predicates, selectivities for the pair of them, multiply that together. And a very common consequence of that particular algorithm is that Oracle massively underestimates the number of rows that will be selected. And a very bad underestimate will result in Oracle perhaps picking a path which says, oh, start here because it's a tiny amount of data and we'll do nested loops in the following order. And of course, that may be a very bad place to start and a very bad order in which to do the nested loops. So let's run up a little test here to demonstrate this. I've got here 10 to the 4, 10,000 rows here. I've got N1 and N2 where I use mod 100. So each of these two columns has 100 distinct values, 100 rows per value. And of course, as you can see, I've declared these two columns so that they are always absolutely identical to each other. Having gathered stats, here's my query. Select where N1 is 50 and N2 is 50. Now we know that there are 50 distinct combinations of N1 and N2. This should give us 100 rows. The optimizer's estimate is 1 row, because it's basically said there's 100 possibilities for N1, there's 100 possibilities for N2. That means there's 10,000 possibilities in all for 10,000 rows. So on average, the answer is 1 row. So that's the basic impact, somewhat extreme example, obviously, but the basic impact of correlated columns. Workarounds to correlated columns. Well, here's one, create an index. This is perhaps expensive and inappropriate, but it's one that works historically. Create an index on those two columns. Now I've followed that with a query which says, select a column that's not in the index so that we can go through the index and go to the table. Select the column that's not in the index and do a count of it. Now, this is a very bad index, so Oracle isn't actually going to use it. However, Oracle can say, your predicate matches the index definition. I can look at the number of distinct keys in the index, and that tells me the number of distinct combinations of N1 and N2. And suddenly, Oracle knows there's 100 combinations, and that the cardinality, therefore, is 100. So creating an index, even though the index hasn't been used, tells Oracle about the cardinality, or the selectivity, rather, of the combination. Okay, we can create the index, but that is, of course, an expensive strategy. Get rid of the index. Oracle 11 gave us extended stats, And the best possible use of extended stats is for column groups. So what I've done here is gather table stats, and I've said gather table stats for columns, and I've specified a single column group here consisting of the column pair N1, N2, no histogram. With this column group stat in place, again, I run my query, N1 is 50 and N2 is 50. Oracle says, I know that pairing, I've got a column group bit of information about N1 and N2. There's 100 distinct values for the combinations of N1 and N2. My cardinality estimate will come out correct. So column groups are a much nicer, lower cost strategy for giving Oracle information about combinations. And this generally is a very good move and a very good thing to watch out for. Okay, so when are your plans bad? Because of serious underestimates, because you've got equality on multiple columns, but you don't have information about the number of distinct combinations that's sufficiently accurate to help the optimizer. Now, the problem, though, is that this is terribly unstable. There are all sorts of things that will break both the distinct keys of index mechanism and the column group mechanism. In fact, anytime I say this breaks if you do X, Y, Z, that statement probably applies equally to the distinct keys of indexes and to column groups that you've explicitly declared. So let's run through a couple of quick demos of the things breaking. So breakage number one. What happens if you query out of range? Going back to out of range, isn't that great? Okay, so let's create the column group. Let's take the example of the column group and say, let's select where N1 equals 50 and N2 equals 101. One of my columns specified is out of range. Oracle has no idea how this actually affects the possible combinations which really exist in the data, but it looks at that N2 equals 101 and says, oh, one of the underlying columns is now out of range, forget the column group, and the estimate goes back to 1. If we had the index created on N1 and N2, rather than the column group, N2 here, I've supplied an out of range value, forget the number of distinct keys in the index. Oracle just throws it away and goes back to the N1, N2, multiply the selectivities. So Oracle gave us the benefit of this correlated columns, the column group statistics, but it breaks incredibly easily. It's even more fragile than the normal problem of moving outside the range. It breaks instantly the moment one of your predicates is a tiny bit outside the known range. So here's another reason to be aware of those queries where the data moves forwards and gets bigger through time, and the queries follow the data. The instant you gather stats, and gathers the keyword there, the instant you gather stats, they're almost out of date. And 10 seconds later, they may be out of date, and the column groups you've created suddenly become irrelevant. So out of range, it's really bad news. Very important thing to keep an eye on. Another effect on correlated columns, histograms. Okay, so here I've created my column group. Notice in my method opt here, I've said I want a column group. I'm not bothering with a histogram on the column group. Oh, by the way, N1, one of the columns in the column group, I'll have a histogram on that, 255 buckets. Okay, what happens now? Oracle's estimate of cardinality says, forget the column group, simply look at the two separate selectivities. Okay, when we've got a histogram on some of the columns in the column group, Oracle says, forget the column group, unless you've also got a histogram on the column group. Okay, that's an important feature. If you've got a histogram on the column group, Oracle can still use the column group. But if you don't have a histogram on the column group, but then create a histogram on one of the underlying columns, that's it. The column group is discarded. And of course, if it applies to column groups, it applies to the distinct keys and indexes. So here we have the index on N1, N2. We put in a method opt which says, just give me a histogram on one of those two columns, right? And when we do our select count of star there, for a value which Oracle should be able to handle nicely, Oracle says, you've got a histogram, I can't use distinct keys. Histograms have a massive override effect on other statistics. So a guideline there, be extremely cautious about histograms. Avoid creating them unless you absolutely definitely need them. And when you do create them, think about the side effect on every single index that you've got. How many of your index number of distinct keys are really important? How many of them might you disable? How many column groups have you created? Have you got a histogram on those column groups that allows you to have a safe histogram on the underlying columns? So be extremely careful. I'm always telling people you've probably created too many histograms. This is just one of several reasons why your histograms might be a threat rather than a benefit. Okay, is null. Now I've got two queries here which look remarkably similar. Select from a table where column 1 equals 1 and column 2 equals 1 and column 3 in one query is equal to a specific value, in the other query is null. Now in this particular table, the stats on the table and the data content in the table have been set up very, very carefully. The number of rows where the first predicate is true is exactly the same as the number of rows where the second query predicate is true. Both those queries will return exactly the same number of rows. Moreover, there is an index on column 1, column 2, column 3. So there's a very precise, accurate, good way for Oracle to say, I know how many rows I'm going to return. I know how I can best get at those rows. So let's see what happens when we start trying to query those data, what the plans look like. Okay, I've got frequency histograms. I've got histogram records for exactly those values. Everything is perfect for Oracle to know exactly what's going to happen with both those queries. Okay? So Oracle says, hey, I can use the histogram. I can use the index distinct keys. I'm perfect to use my index to get at the first query. Second query there, Oracle says, is null. Oh, forget everything I know. Right? I can't use a column group because it is null. I can't use distinct keys because it is null. Everything goes out of the window. Forget my column group. And when we look at the trace file, you can see here that Oracle basically says, the first bit of the trace file, the 10053 trace file, you've got 3 predicates in your query. I've got a column group here, which is a fantastic match for those 3 predicates. I've got a full match on that column group. I will use the column group, I will get the right numbers, and I will give you a good estimate on that query. You go to the second query, and Oracle says, well, I've got a column group which has got 3 columns in it, but you've only given me 2 predicates. Column 3 is null, apparently is not a predicate. Oracle has simply discarded it when considering matches between predicates and column groups. So Oracle simply says, you don't have a relevant column group. And in this particular case, as a consequence, it came up with a ridiculous estimate of cardinality and took a very silly execution plan. But most significantly, the cardinality for those 2 queries did not match when clearly there was enough information in the statistics for that match to take place. So another breakage in column groups and correlated columns. Okay, another general feature to watch out for, and this is one of these things where I can't really say to people, this is how you fix the problem, okay? This is a pattern to be aware of. It's a pattern that people simply forget. It's a pattern also, as you can see from the first line here in my example, it's a pattern that most frequently is likely to appear with partition tables, because people frequently partition data to say there's old data, which perhaps has gone read-only, there's new data, which is the stuff that people are really busy with, and we want to treat old and new data very differently, and we want to keep our new data as small as possible and as precise as possible. So imagine I've got an orders table here, which has been partitioned by order date. And an order goes through a handful, just a few different states. It'll be new, it'll have gone to the warehouse for picking, it'll have been dispatched by the warehouse, someone will have sent invoice, someone will chase up that the invoice has been paid, and then the the order can simply be put to bed, everything's complete, everything's done. So for my orders table, I've got a column which is a status column, which goes through 6 different states. Well, think about what this means in terms of what the data looks like, right? Give this system a couple of weeks, and virtually all the orders that you placed today, all the orders that were new today, will be marked as done. They'll have gone through the 6 steps, they'll be done and dusted, right? And bear in mind, we're partitioned by order date. So that means partitions in the past are almost completely done orders. There may be 1 or 2 or maybe 14 or 16, 20 partitions, if it's daily partitions in the present, where we've got some mixture of done, new, picked, invoiced, and so forth. Today, almost everything you look at in today's partition, or for the first couple of days of the week's partition, almost everything will be new or picked. The current partitions will look completely different from the past partitions. And of course, we'll have typical queries, generally like, show me all the orders which are more than 4 weeks, but are not yet done, right? We'll have things like, show me all the orders from the last 48 hours, which have not yet been picked. They're still marked as new. Show me all the orders that we've dispatched in the last 48 hours. So there'll be lots of queries which look at the past in ways which are different from the way they look at the future. Sorry, the present, not the future. Well, they may look at the future, who knows? So the past and the present are not the same. But what statistics has Oracle got if you gather statistics? Well, if it's not a partitions table, the only statistics that Oracle has got are the average for the table. And that can lead to all sorts of bad estimates when you start putting in queries about what you particularly want to see. The other thing to consider is if you gather stats on this table and you let Oracle decide automatically what to gather, it's almost guaranteedly going to create a histogram on this particular column, A, because you use it a lot in predicates, and B, because the data distribution is massively skewed. And we'll see later on that all sorts of strange things can happen with histograms when you've got something a bit like this. So we have a bit of a problem with this data. I'd just like to run up a quick query. I created some data just as an example. I'd like to run up a quick query to show you a picture of the type of thing that actually physically exists within a database, within a table of this type. So I'm just going to do a trunk of the date placed, and then I'm going to put, pardon me, do a trunk of the date placed and the status from the orders table. Then I'm going to pivot. I'm going to create a pivot which says, put these 6 different statuses into 6 different columns and just show me a count of each status. So my data set, which I ran up on a partition table for this, shows these results. You can see here, I created this sometime about 9 o'clock in the morning on the 7th of September. 7th of September here, I've got a few rows which are new, a tiny number which are already picked. The 6th of September, there's quite a lot of rows which are new, a larger number which are picked. You run back into the past a bit, a week ago, and we're looking here at nothing new, nothing picked that was placed on the 30th of August. So the business is running nicely. There's quite a lot sent. There's a huge fraction which is now in the invoice state, and there's a small fraction paid. You go back another week, and the business must be the mafia or something and gets their debts paid very quickly. Everything's done. Everything's been paid. Okay? And you can see there's this picture, this sort of diagonal patch that goes from the bottom left to the top right of where is your data. And you look at that and you think, all that Oracle's got is something which says, on average, a tiny fraction of your data is new. On average, everything in sight is complete. Well, plus or minus a tiny, 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 tiny fraction. So what does that do when you gather statistics and when you hope to get good execution plans? Now, again, depending on your usage, depending on the data, the estimates you get might be good enough that Oracle still behaves quite nicely, but we have no guarantee of that. So let's take a look at this. Let's pick out all the rows where the histogram, we're going to run up a histogram and say, show us about a column called status. Okay, and sorry, the histogram on this column called status. And here's my set of partitions at the moment. And you can see an interesting and quirky thing here. SysP535, it's an interval partition table, so we get silly names. Sampled 20,000 rows. That's actually the entire set, and has a histogram with 4 buckets. Go back a little way. SysP531 only sampled 5,000 rows. It's got a histogram with 1 bucket. Now, one odd little glitch here, by the way, is that histogram ought, as a frequency histogram, to have been 100% samples since I was using 12C. So there's something a little quirky about partitions and histograms, and people have often complained about Oracle in various versions gathering stats on partitions where it doesn't seem to be necessary. Well, odd things happen with histograms on partition tables. Oracle keeps sort of fixing things and improving things over versions, but you will inevitably run into strange little glitches. So there's our histogram information about this particular table. Let's take a look at user part histograms. Here we can break down into detail what were our 4 distinct values. You can see a very recent partition has invoiced, new, picked, and sent. Go back a few partitions, we've got done and paid. Go back a couple more partitions, everything is done. So we've got histograms partition by partition, which look very different from each other. And then, of course, we've got the global histogram, which basically says massive volume of your data here is done. And then cumulative figures here, by the way, frequency histograms. These are cumulative figures. You can see here relatively small numbers of rows in different states here. So what happens, you might say, ask, when we actually start to query this data? Well, let's take a look. Let's select date placed counter star for status new with a group by. This is what the data actually looks like. Go back, in my case, it was 4 days into the past, and there's nothing new, and there's a total of 9,208 rows. And I've gathered stats in the last few seconds in order to get the stats looking as good as possible. Oracle's prediction, I have no idea why, 36,000 rows. The statistics are as perfect as they could be because I gathered stats incrementally from the moment I created the first partition, inserted the data, and kept on going. Every partition added, load the data, incremental gather. The stats are as perfect as they can be, and the prediction is out by a factor of 4. Now, with a bit of luck, that won't necessarily matter, but a factor of 4 is actually quite a significant factor if you have complicated execution plans. What else can we see? Here's a really weird one. The stats are perfect, okay? So I've run up a query. Have a look at these numbers here. I've queried for the 1st of September. That's from partition 35 to the end of the table. That's why we get this 2 to the, what is it, 2 to the 20, the 1048575 figure there. And Oracle's prediction for the number of rows which the status is new and the date is greater than or equal to the 1st of September is 900 rows. So let's move forward a bit. How many rows is Oracle going to predict from the 4th of September onwards? Right? It can't be a bigger number than 900, but how many is it going to be? Sorry, I lied. It is a bigger number than 900. With perfect stats on this table. 4th of September, partition 36 to the end. Oracle says you've got more data from 36 to the end than you have from 35 to the end. And I've done perfect gathering of stats. Now, partly the reason why this has happened, by the way, is because Oracle has used table-level statistics for the first query, which is because I've got partition 35 and 36 as the only real partitions in the table past the date I'm after. When I query the second query, Oracle says, wait a second, the only real partition you've got at the moment is the one partition number 36. So the arithmetic has worked out differently. Oracle's used partition stats for the second query. It's used table level stats for the first query. And we end up with this strange appearance coming up. Okay, you've had 45 minutes. I will just take a short break. It'll just be 2 or 3 minutes, and then I'll start again. But if you just want to pause and sit back and relax for a moment, I'm just going to go silent for a couple of minutes. Tim, if you want to pause the recording for a moment, I will give you a warning that I'm about to restart. Okay, we now move on to something a little more subtle and a little more awkward to deal with. It's the thing I call lost skew. I'll demonstrate this because it's quite hard to describe without actually having something in front of you. My usual sort of trick, here's a table I've created, 100,000 rows there. I've got this column here, it's a status column. I've used the random number generator to do a normal distribution. I've made it positive, multiplied by 3, and truncated. So this will produce a small number of integer values with a very strongly skewed distribution to it. Okay, I've created another table, which is going to be a very small table. It simply says, select the distinct values of the ID from the first table, the ID status, and add 65 to the distinct values you've got, convert to character. Character 65 is the capital letter A, so what I've got here is just a set of rows which match the possible status codes, ID statuses in the big table, and which simply translate numbers into letters. So a quick check here to see what I've got. So from the table which I've called my facts table, I've got an ID status traveling from 0 to 12, very large numbers of rows at the low end, the 0, 1, 2, 3, tapering off to just a couple of rows there at number 12. And the corresponding statuses table here, I go from 0 to 12, so I've made that match. I go from A to M. And I've highlighted one row across the pair of them. Status 10 and status code K are the same thing. So if we ask for status 10 in the facts table, we should get 55 rows as the prediction. I'm going to create a histogram on this statuses code, this ID status code, in order to make sure that Oracle is aware of that skew. Okay, so having created the data and created the histogram on that data, let's run up a query, and let's take this very simple one to start with. Select from the facts table where the ID status equals 10. Okay, there's my execution plan. As we would hope and expect, Oracle has said, my predicted cardinality is 55 rows. 55 rows, status 10. We've got a histogram on the table. It's not surprising that Oracle has come up with the right value. Oh, I happen to have a bitmap index on this table as well, which is why we've got this bitmap conversion access path there. Okay, status 10 corresponds to status code K. So what I'm going to do is what you do with star schemas, what you do with data warehouses. You have meaningless numbers stored in your big table. You have the meaningful descriptions stored off in your dimension table. Statuses is just a dimension. So I will query for my dimension value of K and join in to my facts table on the status code. So what happens when I do that? So here we go, we join facts to statuses, we join on the ID status, we ask for status code K. Do we get 55 as the prediction? No. The prediction is 7,692. Now, if anyone's really, really good at mental arithmetic and remembers exactly what the previous two screens looked like, they will see that, 7,692 is 100,000 rows divided by, 10,000 rows divided by 13. No, 100,000 rows divided by 13. Sorry about that. It's getting a bit late at night here. Oracle simply said there are 13, in effect, it's not quite how it's done the arithmetic, but in effect it said there are 13 distinct values. That's 1/13 of the data, right? Oracle has lost the skew that we told it about on the status ID on the facts table because we've joined out to the dimension table and we're querying the data by the dimension value, right? And that's pretty much a disaster. Now, in many, many cases, data sets are extremely large. The amount of error you get doesn't mean that Oracle's going to come up with some amazingly different and incredibly stupid plan. But sometimes it just does happen. You've given Oracle information about data skew. The moment you join to the dimension table, Oracle loses that data. It's a symptom, a generic symptom that you can watch out for when some of your big star type queries do something insanely stupid. There's not an awful lot you can actually do about this. one of the first things that you might have said is, well, okay, instead of having that boring little bitmap index on the ID status, the numeric status, let's create a bitmap join index. So here we go. Here on my facts table, I'm going to create a bitmap join index, create the bitmap index, use the status code character here as the index key, join the facts table to the statuses table, and there's my join condition. And now, oh, it doesn't work. I run in the query which says, join here, select where status equals K, and Oracle says it's still 7,692. And the really sad thing about this is Oracle said, do you know what? I'm using your bitmap join index to do this. And look, the predicate says there's this underlying hidden virtual column on the table, and I'm using virtual column equals K. I've actually got a virtual column on the table, and if you could get some statistics onto that virtual column to tell me about the skew, perhaps I could use that virtual column stats in order to get the right cardinality estimate. But unfortunately, when I actually ran the code which said, create some stats on this virtual column, Oracle still ignored that, still came back with the thing, the estimate is 7,692. So design says the right thing to do is query the dimension tables and join to the fact table. The optimizer can't cope. At least the optimizer loses all your skew if you actually take that approach. There is, by the way, one mechanism which is sort of unofficially official that you can use to work around this problem. There's a hint called the pre-compute subquery hint. So I've rewritten my query. Instead of using a join, I've said select from the facts table where the ID status is in subquery. And I've said pre-compute. I might actually want to say no merge as well. Pre-compute the subquery where status code equals K. What happens now is that Oracle does a two-pass process on this query and says, pass 1, status code equals K, that gives me the value 10. Pass 2, optimize for fact ID status equals 10. So in subquery, you can put in the pre-compute hint, pre-compute subquery hint, and Oracle will actually compute the results set from the subquery and then optimize for something which you didn't write. And when we look at the execution plan, two things to notice. The cardinality estimate is 55, and the predicate isn't the subquery predicate, it's the computed result of the subquery, ID status equals 10. Oracle does this itself, by the way, in the Oracle OLAP package. That's where they use the pre-compute subquery. Okay, so that's an important one. Watch out for the symptom, recognize the symptom. There is a mechanism to work around it. It's highly undesirable that you actually have to use something which, technically speaking, isn't really documented, and you know, it's pretty much unofficial. So we move on. We move on to distributed queries. And what can go wrong with distributed queries? The answer is simple: everything. In a distributed query, if you're just joining two tables from two different databases as the very simplest case. First off, if you've got histograms on the remote table, Oracle doesn't look at them. So it doesn't matter how much information you've got about skew at the remote site, Oracle in the local site has no idea about what's going on. Moreover, if you've got function-based indexes which you've created to try and address some of the other statistics problems, Oracle ignores function-based indexes at the remote site. Right? And that includes, by the way, reverse key indexes and indexes with descending columns. So that's bad news. If you've got virtual columns and extended stats at the remote site, Oracle doesn't look at them at all. Right? And those are things we use to solve cardinality estimate problems. Oracle doesn't look at them. And of course, part of that is it doesn't look at the distinct keys of indexes. Right? And of course, it doesn't look at indexes on virtual columns anyway. Distinct keys. Oracle doesn't use distinct keys from indexes as part of the selectivity calculations. In a sense, it's, you know, it's just ignoring, it's treating it like extended stats. It's a column group. Oracle doesn't use the column group if it's a remote column group. And it's slightly worse than that, because if you've got one of these systems like, oh, I don't know, SAP or Siebel or PeopleSoft or whatever, which gives you an average of 65 indexes per table, Oracle only considers 20 indexes on any one table if the table is remote. And now that's actually documented as a restriction. What isn't documented, but is my best guess, is that Oracle uses the last 20 indexes created on the remote table. Which means that if someone happens to create a new index on a table that you're querying, the index which you happen to be using in order to optimize the query might stop being in that last 20 indexes, and your execution plan changes in this database because someone has created an index in another database, and it's an index which you're not using. So some really weird things can happen. If you've got distributed systems, you have to know everything about both ends of those systems. Now, I've put up a few URLs here from blog notes I've written about distributed queries and the wonderful and weird things that can happen with distributed queries. Now, the next 3 slides actually are slides which demonstrate just one of the points about distributed queries. It's just a sort of little proof that Oracle's ignoring histograms. I'm running a little short, a little behind time, so as I said at the start, I'm going to just skip over those slides. So don't worry about that, it'll be in the handout. So here's 3 or 4 slides, whoops, 4 slides about distributed queries. That brings us to the end of problems with actually using statistics. What about gathering stats? Okay, histograms are things which I generally rather hate. And for many, many years I've said, don't gather them unless you absolutely have to. And if you really need them, don't actually use Oracle to gather them, write programs to create them. 12c, however, gave us a couple of new types of histograms, which was a good thing. And 12c gave us a new mechanism for evaluating histograms, which also was a good thing. So with 12c, we've got the top frequency histogram and the hybrid histogram. The top frequency one is like a sort of cross between the frequency histogram and an approximate frequency histogram, which just says there's a tiny bit of data which I'm going to sort of ignore for the moment. What I'm giving you really is a very good approximation to your data, and it looks almost exactly like a frequency histogram. That's absolutely great. And the frequency histogram and the top frequency histogram are things that Oracle gathers more or less free of charge whilst it's gathering the rest of stats. I'll come on to the hybrid in a moment. A bad thing that happened in Oracle 12c, which makes me say to people, well, forget what I used to tell you for 11g and earlier, size repeat has changed its meaning. In earlier versions of Oracle, if you put in a gather method.size repeat, Oracle would say, if you've got a histogram now, I will gather a histogram next time I gather stats. In Oracle 12c, it means if you gathered a histogram last time, I will gather a histogram using the number of buckets which I can see at present. And this has a very nasty side effect. Imagine you've gathered stats on my status column, which had 6 possible values in it. And you say size repeat. And day after day after day, Oracle says, okay, gather stats, it's 6 columns, create a histogram with 6 buckets. And one day when it does the gather, there happen to be only 5 distinct values in sight. Oracle gathers a histogram and says, give me 6 buckets. Oh, I only need 5 buckets because there's only 5 values. And the next day, Oracle says, size repeat. It says 5 buckets here. From now on, I gather 5 buckets. And you don't have a frequency histogram anymore. If you're lucky, you'll have a top frequency histogram. If you're unlucky, it's changed to a hybrid histogram. Right? So size repeat is now a dangerous thing to use in Oracle 12. But gathering a histogram on a frequency histogram or a top frequency histogram is okay in 12c because it's 100% accurate. Now, there is also the hybrid histogram which came in 12c. And the problem with the hybrid histogram, although it's much more effective, it's much more informative than the old height balanced histogram. Like the height balanced histogram, Oracle takes a small sample size to build the histogram. And it picks, as a basis, 5,500 rows, even when there's quite a large number of rows in the table. So hybrid histograms and height balance histograms can be hugely unstable. And so I tend to say to people, mostly with histograms, write programs to create your own. If you know you've got a really perfect chance of getting a frequency histogram, just say to Oracle, okay, you can gather it, size 255. It'll actually be whatever size is the number of distinct values. If you want to. Same with the top frequency. It's safe to gather. Although I have to say with the top frequency, there's currently a bug. It's noted on my blog. It's currently a bug, which means there's a patch you need to apply in order to fix that bug before you gather for top frequency. Let's just show you how dangerous hybrid and height balanced histograms are, how unstable they can be. I've got here a table, typical sort of thing. I've got 1 million rows in this table. This thing here says, get me a mod 10,000, take the square root. So I've got 100 distinct values in this particular table. The small numbers appear a few times. The large numbers, that's getting up to 100, appear a very large number of times, okay? I'm just going to gather a histogram, and I'm going to be silly. I'm going to say, give me a 10 bucket histogram on this particular column. And then I'm going to run up a couple of queries, one which says, show me the user tab calls for this table, show me the sample size you've used and the type of histogram you've got, okay? What do I get from here? I run the gather stats, and Oracle says, I've sampled 5,500 rows from 1 million row table. And the size can get much bigger. It's a hybrid histogram. Just repeat, 5,519 rows. Every time I run this gather stats, my sample is just slightly different from 5,500. So that's one degree of instability. Small sample size, and it's variable. It's about 5,500 rows. You have to have a very big table before that sample gets much bigger. What about the actual content of the histogram? This will show me what's in my histogram. The first time I ran the gather stats, I got this set of results. The right-hand column there, the val column, is the values that are in the table which have actually been noticed and had stats gathered for them. You can see, of course, I've only got 10 values in there out of the 100 possible values. Second gather, the highlighted values are ones which didn't appear the first time. So I've lost some, I've gained 4. A gather again, the 7 values highlighted there are values which have not been seen before in a histogram. The fourth time around, only 1 value which I haven't seen before. But every single time I gathered stats, I got a different set of stats, a different pattern in the histogram. And that can make an extraordinary difference to the stability of the queries you run. So hybrid and height balanced histograms, you have a problem. If you let Oracle gather stats with its default sample size, it's a small sample, the histograms are very unstable. On the other hand, if you do something which says, give me a big sample size in order to get a stable histogram and actually do the gather, it takes a long time to gather that histogram because of the sorting and aggregation that Oracle actually has to do physically to be able to create that histogram information. So you've got no good choice really, which is why I've said to people in the past, if you think you really need a histogram, write the code which models the histogram. Create, and typically what I actually used to say to people was, create a frequency histogram, which is a good model of what you want Oracle to believe. And we'll have a look towards the end of the presentation as to how easy it is to create histograms. Okay, I did mention that there is a bug. In 12C, I've said top frequency histograms are basically free of charge. It's 100% gather. It happens whilst Oracle's gathering the rest of the stats for the table. It's basically free of charge. It's accurate. It's stable. There is one problem, and it's a very specific sort of problem, which basically says there's a bug in Oracle if the values that Oracle discards when it's saying, I can only gather stats on 95% of your data, and there's a little bit which I have to miss because there's this little bit of garbage that's not really going to make much difference. It ignores a little bit round the edges, deliberately so, and gives you a very good frequency histogram, which is a very good model for the rest of the data. But If one of the values it's ignoring is the high value or the low value for the table, those values get brought back into the histogram. And as they get brought back into the histogram, Oracle loses 2 of the histogram values. And currently there's a bit of a bug, which means the histogram can effectively be extremely garbaged as far as you're concerned. It's only in very special cases, though, where you've got a small number of values which are higher than the highest popular value. I've actually modeled this. Again, I think I better just skip through this very, very quickly. So I've created data here. Half my data has the very special value as character string 999960. But there's a few rows with a character string which is a bit higher than that in value, and the rest of the data is virtually unique. I've gathered stats here, said to Oracle, give me a histogram with 254 buckets. And Oracle has created a hybrid histogram because it said, well, actually, the data which is lurking around the edges is, hang on, did I say hybrid histogram? This applies to top frequency and to hybrids. Oh, sorry, it's created a hybrid, but the problem applies to both hybrids and top frequency, okay? In this case, it's created a hybrid histogram. You can see here, we've got this column hybrid histogram, the small sample size, but look at what we've got. And notice the 2 highlighted columns. Now, the way we read this histogram data, this is a value that it's found as a low, as it's in the first value. This is the value, this is the number of rows in the bucket. And we go up through the values which are stored in the table. And here, between 999675 and 999999, which is the highest value in the table, we jump from a sample where we've got up to our first 2,500 rows, and we jump to 5,400 rows. This histogram says to Oracle, half your data is between these 2 values, 999675 and 99999. Half your data is there. And that is correct. Half the data is there. However, we have lost the fact that that data, that 50% of my total data set, is specifically the one value. Because Oracle said, when I created my histogram initially, I had this massive spike at 999960, but I had to throw it away so I could bring in 999999 in the final histogram. So we've got a massive error in this histogram. But it is at least an error which is somewhat rare. It's an error which only applies in very specific circumstances, which you might recognize. Again, you either patch it, and I've got some details here about the patch, you either patch it or you write a program which creates the histogram, which tells Oracle what it needs to know. Okay, histograms, don't gather them unless you know they're going to be frequency, or if you've got the patch top-end histograms. There's a couple of extreme cases where you might even then want to write your own programs, okay? Don't use size repeat in Oracle 12c. Basic setup, this is what I do with people. Find something that's easy, that's almost always going to be correct. Set the global preferences for stats collections for all columns of size 1. Now, having said that, I will also say, don't just do that on the production system without testing thoroughly first, okay? This is a significant change to your strategy. This is a big picture strategy. It's also flatly in contradiction with what Maria Colgan says, so you know we'll have to fight it out one day when she's over in the UK. Set table prefs where you know you've got a good case for a nice, safe histogram that's safe to gather. Set table prefs, and then let Oracle gather auto. And you can set a method opt in your table prefs saying, for this table, all these columns it's size 1, these columns it's size n, maybe it's size 254, okay? So we do something very, very simple and identify the tables which should have histograms. And really, it should only be a very, very few of them. And if they're not frequency or top-end histograms, you write scripts for the really strange ones, the ones where it's important, but you have a stability problem. What about indexes? More solutions coming up. Sampling, Oracle says with auto sample size, that means 100% for tables. For indexes, it typically means I will really sample it and it's 1100 blocks. That does vary for when you've got very small indexes. Oracle does a full scan on a very small index up to 5,000 blocks. It does a fast full scan sample on approximately 1,100 leaf blocks if you're doing auto sample size, right? And it doesn't behave terribly nicely when it's doing it anyway. Now, various problems with that, of course, instability amongst other things because the sample size is so small, right? And of course, if you decide you want a 100% sample or a much bigger sample, you pay the price of doing all that work. So you've got various impacts. Again, it's like histograms. Small sample size is quick but unstable. Large sample size may be much more accurate, but much, much more expensive. I do have a comment here. Nigel Bayliss came up with a reference for me, which was there is a patch which is available in various versions of Oracle, which you can get hold of, but actually I haven't yet installed that to see what happens where Oracle does a better index number of distinct key sampling. I'd love it if someone actually got around to getting that installed and doing some testing on it. I will eventually manage to do that. The things I do with indexes, it helps if you create a column group on the index definition. In fact, in many cases, you may find you solve various performance problems by creating index column groups on the index definition itself and then decreasing leading subsets of that index. So if you've got a 4-column index, a column group on the index definition, if it's really important, ensures that Oracle gets a good figure for the number of distinct keys. But then, perhaps in many cases, more importantly, the first 3 columns, the first 2 columns as well, because if you make partial use of indexes, you need that information. It can be enormously helpful. You may have problems with clearing out dirty blocks. There was a recent example on the OTN database forum recently, where possibly because they had a lot of change and because they were doing sampling, small samples on very large indexes, they occasionally hit vast clean-out type problems when they were running queries. So maybe occasionally you just want to do force a full scan on some indexes to make sure that you have cleaned out data which is by now 3 or 4 days old and could cause some read consistency overheads that you don't really find desirable. And as ever, I'm going to make this comment ever again, Oracle gives us APIs. Set index stats. You can write code to create index stats if you think it's either unstable or too expensive to get good index stats. Clustering factors. Another problem with indexes. The clustering factor is often too big, which makes Oracle think the index is not very good. You can work around that in Oracle 12 because Oracle lets you correct this automatically. Oh, actually, Oracle 11 lets you correct it by setting a table cached blocks preference, right? Which says to Oracle, when you're calculating the clustering factor, allow for the fact that the data is perhaps a little bit scattered as you walk through the index. By default, Oracle says, every time I walk from one index entry to the next, if I'm jumping to a different index leaf block, that means I must be reading a whole new table block. So the clustering factor, the table cache block says to Oracle, if the index tells you to jump to a new block when you're doing this calculation, just check a little bit of your history in case it's a block you looked at very, very recently. So Oracle 11 allows us to address this problem with the clustering factor, making Oracle think that a slightly scattered data set is massively scattered, right? Global prefs or table prefs. I'd like to do global prefs or have a new default from Oracle, but certainly set table prefs. There's a sample statement there setting the global prefs there to 16. Default is 1, maximum is 255. 16, in my view, is actually quite a good default value to take, or if you're on rack, 16 times the number of rack nodes that you actually run against this table. And just occasionally you might want to say, well, let Oracle decide for itself, use the auto table cached blocks size. But we can address the clustering factor on indexes, okay? It's important to do that if you want to get a better chance that Oracle chooses the right index in different circumstances. Table sampling, very good thing, right? The sample is actually 100%, but really what it's doing is don't do an aggregate to find the number of distinct values for each column. Oracle's got an approximate NDD mechanism which says As you're scanning to count and find the number of lows and highs and all the rest of it, the min and max, you can do an approximate number of distinct values for each column, right? This is a very, very good thing, almost always, except there are a few cases you need to watch out for. You'll see this, it'll happen to you if you hit the problem. If you've got chained rows in your table, as Oracle's doing its scan, which is this rapid calculation scan of the table, it will follow chained rows in real time. And you can do a massive number of single block reads when you think you should be just doing a brute force direct path table scan. Index organized tables with overflow segments, it's a catastrophe. If you've got virtual columns, it can be a total catastrophe if those virtual columns are expensive to calculate. I put up here a URL to a blog note I wrote about the problems with IOTs and overflows, so you can follow that one up if you want. The same sort of thing happens with chained rows. There was an example on OTN, the database forum, fairly recently, which said, I created an index on this table and suddenly it took hours to gather stats, right? And when prompted, this person supplied the index definition, which was this. It was, look at a clob which contains an XML and then call a PL/SQL function which extracts something from this clob. Right? Well, when you do your scan, which examines every single row in the table, this particular function has to read every single clob and analyze and extract data from every single clob. So he was taking hours to examine every single clob. Now, in this particular case, the best strategy is probably to have some code which says, when you insert the clob, do the analysis at that moment and actually populate a real column. If you absolutely need that, that's probably the efficient thing to do, then create an index on that particular column. So other cases, a trigger might work, possibly clobs. I think you can't access clobs within triggers, so the front-end code probably, or the wrapping PL/SQL code that loads the data would actually have to do some work to prepare a real column in this specific case. Of course, you might say, there's a workaround this. We can avoid the dangerous columns. We can say to Oracle, gather stats on these columns, but not on those columns, right? The only problem with that is that it doesn't work. Again, I've got a demonstration of this. I'll let you read it. You can actually say to Oracle, I've got this table with 200 columns in it, but I only want you to gather stats on these three columns, these two columns, right? That looks like a way of working around this dangerous columns problem. Unfortunately, it doesn't work, right? Now, I'm going to skip over the next 3 slides again, because these slides are just a demonstration which says, unfortunately, if you say to Oracle, just gather stats on a couple of columns, Oracle still gathers some stats. It counts the occurrences of every single column in the table, which means you still have a massive performance threat if you've got one of these unlucky objects. Okay, so we need Oracle to give us a way of saying, really, truly, if I say just gather stats on columns 1, 2, and 3, we only ever work on stats 1, 2, and 3. Now, I'm nearly at my deadline, so what I will say is just this closing thing. Oracle 12c gives us a fantastic reporting opportunity. When you're gathering stats, it's really important to know, where did the time go if you can see the time climbing to something that's totally unacceptable. You can't really get a safe handle on that. I've faked around it in Oracle 11 and earlier versions. In Oracle 12, you can actually just run off some standard reports that Oracle gives you. I've got the code sample here, set up a few output formats, DBMS stats, report stats operations. And I've said here, show me all the stats operations since yesterday. Well, one of the stats operation is the autostat gather operation, right? A whole autostats gather, whatever it did, however long it took, comes up as a sort of one-liner in this report. But then within this report, you can say, oh, that auto gather stats job, it was operation 7,332, DBMS stats, report, single stats operation, this stat operation ID. Give me everything you've got about it. And the report you get from this will actually say things like, this table, 3.5 minutes to gather stats. This index, 2.5 hours to gather the stats. This index, 33 seconds to gather stats. Every single object will be reported separately, along with, by the way, things which say this gather failed, and here's the reason why it failed. So if you haven't come across it in 12c, do take a look at this, because if you're having trouble gathering your stats in the automatic overnight job, this is the thing which will tell you where the time has gone, and it will tell you easily and precisely where the time has gone. Now, at that point, I've hit my time limit. I've overrun for a couple of minutes. There are a few slides left, but I think I really ought to stop and let the next person themselves set up.
Yeah,
Thank you very much, everybody. I hope that was helpful.
Fantastic. Thank you so much.